we are going to use this package to run some simulations and then look at real data and then play a bit more in the app just to see how changing certain things is going to influence our estimates. And today we are especially concerned about this P, probability of availability. So after this intro to the behavior and how we are going to think about them, let's open up the next file, which is day 2, number 3, removal. We load some of the same packages as we did before. So bsims, we're going to use that to simulate things in this little landscape. Then the detect package is what we are going to use to fit some of the models we are going to discuss today. And then for the real data, we are going to use the JOSM data that you are now all familiar with. This set seed is useful if we want to make sure that what you see from my computer is the same as what you see on your computer. So there is no unexpected mismatches there that would throw us off when we are looking at some of the estimates and the images. So once we run this first line, that is just really going to create this rectangle 1 by 1 green square. There's nothing in it yet. We just initialize the landscape. So if you think about how to use that for your own purposes, and if you need something larger, then obviously you can increase this extent. For example, if you have individuals that move around a lot, or just your detection might span more than this extent, then you need to think about this. But usually for bird purposes, I thought that this 1 by 1 square kilometer is usually sufficient. And so 10 means the units are in 100 meters, because that's how then we can easily translate between these numbers and hectares. If you plot, this is the green forest. Now let's put some individuals inside. So we need to use L, the landscape, as the first argument for bsims populate. And density is 0.5. That means every 2 hectares on average, we are going to get 1 individual. So in a 10 by 10 area, we expect to get 50. Why we see 52 here is because this is a random number with mean 50. Because we often think in terms of a Poisson regression as the first probabilistic model around our counts. That's why this is the default, but you can find ways of just introduce here a more over-dispersed distribution like negative binomial, or just fix it to 50 exactly. Now, if we plot this, then we are going to see the nest location. So this is what those crosses indicate. So individuals are going to move around their nests. Or if we don't specify any movement kernel around their nest, then they are just going to be there all the time and do their vocalization at the exact same location. We can print out the nest location. So there are these functions starting with get underscore something. These are all just going to access some things in this simulation object that otherwise you would need to understand what's inside. This is just pulling out the relevant bits. And here what you can see is I, that is the ID for an individual. S, that is the stratum. Right now it says age, which means habitat. We didn't include anything like road or edge. That would be here, where the nest is located, which habitat stratum that is part of. XY, that is just the coordinates for the locations. And we'll ignore G for now. So if we want to extract abundance or density and divide the two to get area, there are functions for that: get abundance, get density. Now, if you introduce some vocalization into this, then we can say, use this A object, which was our population, and we set vocal rate to 0.5. That means on average, every 2 minutes, there's going to be one vocalization event for each individual. And these individuals are going to be independent of each other. And we want to run the simulation with respect to their behavior for 10 minutes. So this is going to be the total duration. And we can go shorter later. So we're just going to look at the first 3 minutes or first 5 minutes, but we can't easily extend it beyond 10 minutes. So this is where you need to decide what is that maximum duration you would want the simulation to happen over. So once we run this, then we can see the printout from this object B, which again says 1 by 1 landscape, no stratification, 52 as total abundance, and we had a duration of 10 minutes. And now if we plot this, plot B. Then we see not just the crosses, but also dots over the crosses. And that just means the individual is now there. If you introduce movement here, which we haven't done, but once we go back to the Shiny app, that's going to be easy to do that, then you would see those little lines around the nest location here when you plot this object. So what we are really going to be interested in is this get events function. So we take this object B and get the events. So what we see here is the locations of where this event happened, the time when it happened. V indicates if it was a vocal event or not. So when it is 1, that means it was a vocal event. If there is movement involved, which is kind of follows the same process and is independent of the movement or the vocalization, then you're going to see some zeros here. And then also the corresponding location where at the end of that event, the individual ended up with, and I, that is just the individual ID. So this way we can link it to the nest locations, and these are going to be between 1 and 52 because that's how many individuals we have in the landscape, and all of their movement and vocal behavior is going to be stored here, ordered by the time when it happened. So this V object has 253 vocalization event for these individuals. So 253 divided by 52, 4.8 divided by 10, 0.48. This is what we would expect based on vocal rate 0.5. Every one of those over 10 minutes vocalized on average around 5 times. So this is what get events is going to return to us. There is no detection involved in this. So these are going to be all the events that then an observer will be able to detect. And that is going to be a function of the distance between the observer and this location, if that makes sense. So now with this get events data, we have pretty much everything so that now we can look at these detections and how we can get back this 0.5 One approach would be what I just did, take all the events, calculate the mean, and we get a ratio. But we are going to need something more than this, because in reality, we don't get such a nice event table presented by us, by the birds. They want us to work for this data, and so we won't get all the events. We are just going to have parts of those, and we need to work with that data set. So this is the survival model, again, that we discussed previously as part of the slides. And there is a plot method for these events table, which is going to be familiar. This is where we left off. One of the last slides showed you this image. When you have the individuals as horizontal lines, their events, vocalization in this case, are the dots on the lines, and then the first event is the field dots. If you connect these dots, this is the accumulation curve we are looking for. Okay. So here we are lucky because we knew what the rate is. We did the simulation. So we are not trying to estimate it yet, but just put that line on top of the events and see if that kind of matches what we would expect. It's not perfect, but there is some stochasticity involved in this simulation. So that's why the line and the real, well, the simulated data differs somewhat. So what is a way to get the first detection for every individual? You might or might not be familiar with this handy little function called duplicated. So if I have a vector, say 1, 1, 1, 2, 2, and I want to know which elements in this vector are duplicated, then I'm going to see false, true, true, false, true. And if I take the opposite, which is with this exclamation mark, then you're going to see true, false, false, true, false. So if I want just the first mention of the ones and the twos, then I can use this non-duplicated expression to find those. So that's what's happening here. We take that V data frame and find the non-duplicate elements of the individual IDs. And let's call this V1. So now we have only 52 rows in this table. And if we look at T and go back to this plot, then T goes on the x-axis. So that's where we have the first events. And then the y coordinate is just the cumulative number of which individual we are talking about, like the row IDs, 1, 2, 3, 4, 5, and so on. So this is how we get this plot. We look at the first detection of every individual. So now from this table, we can also extract this information. So this vector now, this T column, is going to be time to first event. So we can use this data and fit an exponential distribution to it. So this fit dist is a function where you can kind of fit all kinds of distributions to the data with kind of a constant parameterization. And then the estimate is going to tell us what is our estimate for phi. So our original value was 0.5. Now we want to see what this phi hat looks like, and it's 0.425, which is pretty good given our sample size. And also there's an easier way to do this. So the mean of the time to event data, and the inverse of that is going to be the same number. So in this simple case, it's quite easy to get the mean time to event, and then the inverse of that is going to be the rate. So the rate is the inverse of the mean of the exponential distribution. So once we have this notion of how these events happen and what kind of distribution we could use to describe that, then we can assume a parametric form, which is going to give us an estimate of phi so that we can approximate that line of how the first detections accumulate over time. So if we plot only the time to first detection, so these numbers here, V1, T, then here's this rugged histogram. And then you can see the expected line in red and our estimate based on the data in blue. They are pretty close. So this is how you think about the exponential distribution behind these time to events data. And then the rate kind of dictates how this curve is going to go down. So this is the probability density function of this exponential. And we can now turn that around and visualize the cumulative function, which looks very similar to what we had before when we just plotted V. So now you see how these two are connected. Here we have individuals on the y-axis. Here we have probabilities. So if we only observe part of the population, say 20 over 1 minute, then based on that number, and if we can estimate this curve, we can figure out how far it's going to go. So by taking 20 and this probability here, we will be able to extrapolate and see what the max might be. So where P would be 1, that's where we would have our abundance. So this is how this curve is useful for us to estimate abundance when there is no other process involved. So here the different lines. We have the empirical cumulative function, which is just connecting the dots. Then we have the expected, which is our 0.5 that we use to simulate the data, what we estimate from fitting this exponential distribution to the time of events. And then this is the binned version. And I'm just looking at binning the data right now, so we are not using this yet to make any kind of estimation, but just then kind of showing you how 0 to 3, 3 to 5, and 5 to 10 minutes, which is going to be how we are collecting the data in multiple time intervals. And what we do there for removal modeling is that we write down the first detection of every individual and which time interval it happened. So you can see in this left-hand side that over 3 minutes, we observed closely 40 individuals, then an extra 10, and then some more. So those new individuals, how far you go in the next step, this is the information we collect in the multiple time intervals. And why it's called removal modeling is that whatever we have detected in the past, that is now removed. We are only looking at new stuff. So what number of new individuals we can still detect if we continue surveying, and then during an extra 5 minutes, we only have like 4 more individuals. So whatever was in the past, that is removed from the population. And this kind of estimation was used not just mentally removing individuals, but when you hunt animals, by hunting them, you remove them from the population. So as you see less and less of them in the future, that means how that amount is decreasing, you get an idea about how many more there is out there. and then you can use that information to manage the population or control hunting rates. So this is the history behind removal sampling. And this chunk just shows you how to fit a survival model to this time to event data, which is something we won't really use today. It is just for reference. So what you do there is you have your time to first detection, and sometimes you know that the species is there, but you haven't heard it in that 1 minute or 3 minute or 10 minute. So you need to then create an indicator, which is going to tell the survival function when it's 0, that event happened outside of the time frame you were looking at. And this is really important in survival modeling, and this is called censoring, when you are following patients and how those events, like a recurrence of a disease happens or they might die. That is an event you record when that happens, and at some point you just stop the study, but not all of the patients might have developed symptoms or died, and that way they still going to have that event eventually sometime in the future, but you're not following that anymore. And that is what's called censoring, and we just put a 0 there. So in our bird case, this 0 might indicate we listened to 10 minutes and no one showed up, but we're pretty sure birds are there, but we just haven't listened further. And then once you have this data, how to put that together in a survival object and fit a surv reg with some distribution to it. And then you would get a prediction for this rate that we are interested in. So this is just a side note how you would use time to first detection to fit a survival model to it, which for some of you might be quite useful. So let's go back to the removal model, which is concerned with this binned data, as we saw. So the time to first detection data and the survival modeling is a different kinds of data set, and that might be available to you if you are listening to a recording. So there's a way to go back and record the exact second, or maybe in the field you do that, but that's not always the case. Usually we only have the binned observations without the exact time when that individual was detected. And this is where removal model comes in. So the data, what we get, looks like a vector of counts, like here. At location I, you get a vector of counts, and these are the new individuals. So if you have a vector of 2, 1, 0 as your observation, y, that means in the first time interval you detected 2 individuals. The next time interval, on top of these 2, you heard 1 more. And in the last part of your survey, you heard none. So this is the information we would have. And often we would also have the endpoints of those time intervals, like 0 to 3, 3 to 5, 5 to 10. So this is the information we have from the field collected data. So these endpoints are these J's. And in the detect package, there is a function called cmulti. And this naming reflects 2 things. C stands for conditional maximum likelihood, and we see what we mean by conditioning. Multi means it's a multinomial model. So these counts are going to be related to cell probabilities in a multinomial model, and those cell probabilities are dictated by these differences in the curve. So we take the cumulative density function and calculate these differences between the endpoints. And these probabilities end up to 1, and the proportion of the individuals we expect in the first, the second, and the third interval are going to be proportional to these differences between points along the cumulative curve. So I'd like to stop here and make sure that everyone is okay with this statement and you fully understand this part. Any questions? Anyone who would like me to explain it better or different? 1, 2, 3. I take silence to be yes. We fully understand this. And that also means that removal modeling, the concept is really straightforward. You keep listening, take note of new individuals, and then if you assume an exponential distribution and no difference across the individuals, then this is the line this accumulation should follow, and as a result, we can estimate this.
Peter?
Yes?
Could you use just the data to approximate different distributions, like the empirical distribution, and not just to... I'm thinking of distance sampling, for example, in which the shape of the relationship and how the counts vary with distance is not important per se, as long as you can adjust a curve to your data, data world.
Yes, if you have more refined data, which sometimes you have, like the exact distances in that case, that is always going to give you more flexibility in what kind of models you can fit to the data. So if in this case you have time to first detection and you can also bin that just gives you two different ways of estimating, or maybe more flexibility into how you can use the data to estimate under a different model. Because what we lose here by binning is all that information, right? Which is because it happens so fast, we don't have time to put everything on a paper. But when you have more time to analyze a session, then you might get that information. And if you spend more time with transcribing the data, then that extra information is going to help you to estimate something better or something more. So I just went back to this chunk because there was one step I didn't quite fully explain. So we saw what this time to event involved. So these are our detections for detection times for the black dots. And now the binning happens as we take these breakpoints, 3, 5, and 10, and use the cut function. So we'll have this I. This is how we do the binning. Include lowest, that just means that this endpoint of the first interval is going to involve the lowest number there. Otherwise, it would be an open interval in that regard. So 0 to 3, 3 to 5, 5 to 10, and this is just the counts that we would observe. And in reality, this is really high, but because we are now looking at 52 individuals in this simulated landscape, this is how it comes together. So that's the data we are going to use here and the breakpoints to fit the removal model. So we create a matrix, which is just the same information as in this table, but we put it in a matrix. So this is one row in a matrix. And if we have the same protocol, and we might go to station number 2, station number 3, we would have those as extra rows in this Y matrix. We would need a D matrix, and by D, I don't mean density. This is the design, or I don't know a better word. I just keep calling this D matrix without realizing that we also use capital D for density. So there should be no confusion. This just captures the breakpoints for the time intervals. You can see 3, 5, 10. So if you have a protocol which would say 0 to 5, 5 to 10, you would have only 2 columns. So this is what we saw in the JOSM real bird data set. We had the same breakdown. That's why I'm using it, because once we get to the real data, this is going to be familiar. 0 to 3, 3 to 5, 5 to 10. We only have one row because we made this one landscape only. So this is the 2 matrix we need. But you can now imagine both of these have multiple rows, and that can be also supplied. That can be easily supplied, I would say, into C-multi. Why we use a different function here is because we have only one row. And if you only have one row, the real function is going to complain, hey, you can't really do this. And that's why we use C-multi, but otherwise you would be looking at this function with a nice formula interface. As for the real data, you will see you can do something like this. Y given D follows intercept, use removal modeling. So this is how you would usually fit the removal model to a real data set. But because here we are only looking at one row, and I said, well, if you have one row, you shouldn't consider this option, then the C-multi-fit is going to give us what we want, the coefficient from the removal modeling, and then we are going to talk about why we need to exponentiate that. So let's see what that looks like.
Peter?
Yes?
There's a question, maybe you can clarify what a row means. It's not the species, it's the individual detections, no?
Okay, so what we have here in Y is one row because we had one landscape. And so if you have, you can think about this one landscape as one survey. And this is a special survey because we could detect everything that was in that square. If you are doing a real survey, then distance is going to have an effect, or you might decide to just mark detections from a predefined area. So one row in this sense means a survey event. So it is not an event that like the individuals behave in certain ways. It's a survey event that an observer goes to a place at a given time and does a survey over 10 minutes.
Okay, so this clicks back with what you said about replication, that in a real situation, how you will get enough data to fit this distribution is by having replicate site and then kind of
yes,
all the information,
in that
same
regard,
as you would
can
do with distance sampling, right? With
yes,
you will pull all detections to create one detection function.
Yes. So in this sense, each row represents a different survey. And you can think about survey as at the same location, I go back and repeat it every day or every week so that I can see how things might change over time. Or you might come back every year to the same location, or you can visit different locations. And that would both add rows to the data. And the columns, so if you now take the sum of this, which is 52, that is what we were using before in the GLM. When we had Ovenbird counts as Y, that was sometimes 6, more often 2, 1, or 0. So this total is going to be your total number of counts that we used in the naive GLM. Now the reason why we have multiple columns is because we have these time intervals. And because we only capture the new individuals, the sum of this is the number of distinct individuals that you detected during that 10-minute survey. Does this make sense?
Yeah, so I had another question with that along the same line. So each row is a survey, and I that makes sense. Does that mean that these 37, 12, and 3 are aggregate of all species? So no matter what the species is, that is 37 individuals regardless of species? Or is this, do you have multiple matrices for each species? So at site 1 for this one row, you would have one matrix for ovenbird, one matrix for black-throated blue warbler, etc.
Yes, it's the latter, although we've looked into using the total number of individuals as a metric. If there is a reason to assume that they should behave similarly, or you're interested in the total abundance of all the bird species, you can do something like that. But in this case, and in the real data example, these are all coming from data for a single species. So think about the simulation that we did, rate 0.5, that's an ovenbird. Ovenbird sometimes have 0.8. And at least from estimates. So this is just one species. So if you have multiple species, then their availability might be different. And so you would need to treat them independently.
Yeah, Peter, so this really brings the opportunity for something that was itching me. So I was wondering if the time to first detection could be a species-specific trait in a way, right? Because, I mean, detection is not just a nuisance, right? There's ecological things driving how detectable a species is, not even perhaps phylogenetically correlated, right? So I don't
Yes.
think it makes sense to pull everything because each species will have their own distribution or mean time to first detection, no? And that could vary with habitat, with observer, but it will be a baseline or an intercept if you want that is likely species specific, no, in some way.
Yes, I'm going to show you some results later on once we have Q also in the mix, how these quantities relate across species. So when you look at 80 or 90 species, then you're going to see certain patterns, how groups of species might have higher or lower detectability because of them being residents or migratory species, and that just influences their phenology relative to when we tend to sample them, or how big they are. And if they are big, you might hear them from larger distances. And that is really neat, just to know that this is a pattern and that's happening, and that kind of validates that, okay, these estimates are not totally garbage. But there is also an aspect when it comes to rare species, and we can't do much with their data, or we might have a bunch of occupancy data on a species, but really we can't find any kind of distance sampling. In that situation, you might look at closely related species and how their estimates might help you, because there is reason to assume their close relative is going to be similar to them.
I was going to ask if that has a phylogenetic signal. That would be really cool to look at.
So it's phylogenetic to some extent, but also comes down to anatomy and physiology. So if you can
perhaps you could adjust,
those,
account for the traits and see what is going to be explained by a phylogenetic relation matrix or something.
Yes. So we did phylogenetic regression and also use these trait variables. And that's a pretty cool paper, if I'm allowed to say that about one of my own papers, but that was really neat. And it took us several years because it was just brewing in my mind. And at some point, it was just time to kind of, like a cat with a hairball, it just came out nice and round. All right. So going back to the data, hopefully you can all see the linkages, how we go from the events that are happening in the forest and their timing. And once we bin those, then we get this count from one survey of a single species. And now if you do replication, you get more and more rows. So that is what we will see soon for the real data part. So right now, just quickly going back here and see, we had our true value, because this is bsims, we can control what the true value is. Time to first detection, 22, that's T21, time to first detection. This is just my way of referring to this. 0.425, this is when we fitted the exponential distribution to the first detection times. And this is our estimate from the removal modeling. So when we took this 37, 12, 3 data and knew these breakpoints, we got this, which is very close to what we would get based on the time to first detection. And also their similarity is just another proof that this is probably what the data is telling us in this case. So why it's not exactly the same as the true number, it may be because our sample size in terms of the number of individuals here is low. So if we do replication, then we expect that this estimate is going to improve. So you need either to listen longer, but then you might risk that it's going to be not mourning anymore, so their behavior might change. So you can't just indefinitely keep listening, because that's where heterogeneity come in. So instead of that, you can fix your timing of your surveys and repeat over time at the same times of day, or repeat over space. So now to put everything together before we go to the real data. So this is what our cumulative curve looks like, the step function from the time to event data that we simulated. The real one, the exponential, and the binned data now added to the lines, and that looks quite reasonable. So it's not going up too quickly, or it's not too shallow. So it's about right, what we would expect based on a limited data set. So if you want better estimates, then oftentimes you need more information, and that involves replication.